Hi, let's talk about series. First, we're going to discuss what series are, just a basic definition and introduction. Then we'll talk about what we do with series. Mainly, we want to find out whether a series converges or diverges. Then we'll look at 3 special types of series. This is going to be the first lesson in a series of lessons about series. So let's get started. First of all, what is a series? We were just looking at sequences. If we have an infinite sequence and we add up all the terms of the sequence, that's a series. We use sigma notation here. This means that we add up all the terms from n equals 1 to n equals infinity to get a sum. In order to introduce you to the concept of converging or diverging series, we need to first look at the concept of a partial sum. We call Sn a partial sum. Sn is the sum of the first n terms in a sequence. So for example, if we have a sequence 1 over n squared, S1 would be simply the first term, the sum of the first term. So it's just 1. S2 would be the sum of the first 2 terms. So 1 over 1 plus 1 over 4 is 5 over 4. S3 would be the sum of the first 3 terms. 1 over 1 plus 1 over 4 plus 1 over 9 would give us 49 over 36. So these are partial sums. We're trying to build up to talk about what a series is, which is when we have a sum of an infinite number of terms, not just a finite number of terms. So look at the sequence of partial sums themselves. Like what we were just doing with 1 over n squared, we were calculating S1 and S2 and S3. And those numbers themselves form a sequence. We calculated the first 3 here. 1, 5 over 4, 49 over 36. If we were to keep going, we're just adding another term to the sum that we already have to get the next partial sum. This is a graph that's allowing us to visualize what's going on. The green dots along the bottom, those are the actual term values in the sequence 1 over n squared. So 1 over 1, 1 over 4, 1 over 9, 1 over 16, and so on and so on and so on. You can see that those values are getting smaller and smaller. The partial sums are the numbers that we get when we add up the first n terms. So, like we said, S2, for instance, is the sum of the first 2 terms. S3 is the sum of the first 3 terms. So we can see that the sum is getting bigger because we're adding positive numbers to a sum that's already there, and it's getting slightly bigger, but it appears as if it's leveling off. The sum appears to be reaching a limit. If that's the case, and this is the notation for it, the sequence of partial sums as we go from 1 to infinity, if that is equal to a limit, then we say that the series converges. And if it doesn't converge, then it diverges. The only way we could actually have a series that does converge would be if eventually we are adding on terms near the end, which are 0. So it would mean that the limit of an would have to be equal to 0. You can see 1 over n squared goes down to 0, which means that we're adding 0 onto Sn to get to the next partial sum. And it doesn't get any bigger if we're adding 0. And that's why it levels off. That's why it reaches a limit. The first special series that you see is called the harmonic series. try to remember this. We will often see the harmonic series. It's just 1 over n. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, so on and so on and so on. This seems like the one we just looked at. The last one was 1 over n squared. The last one converged. But this one does not converge. This one actually diverges. Difficult to understand, but it does. It diverges, and that's all you need to remember about this. Is there a proof? Yes. Are we going to look at it now? No. I wanted to show you the harmonic series before I showed you this theorem. On the last page, I mentioned that the only way a series can converge is if the limit of the nth term is equal to 0. But it's important to realize that the converse of this theorem is not true. And what I mean by that is, if you find that the limit of a sub n is equal to 0, it does not necessarily mean that the series converges. It could still diverge. And that's why I wanted to point out the harmonic series. Just bear that in mind if you're ever confused about this theorem I just told you. The harmonic series does have an nth term formula, 1 over n, whose limit is 0. But the harmonic series does not converge. It diverges. Every converging series has a limit of a sub n which is equal to 0. But just because a series has a limit of a sub n equal to 0 doesn't mean it converges. If it's raining outside, then there must be clouds in the sky. But it doesn't mean that if there are clouds in the sky, it's raining. Deep thoughts. Geometric sequences and series are a special type, and we saw this before in our last lesson. When you go from one term to the next in this type of a sequence, you're multiplying by a number. We call that the common ratio. It's like an exponential function, where that number is the base of the power. So in this case, the number is 3. To get from one term to the next, we always multiply by 3. 3 is the base of the power, and n is the exponent, or it's in the exponent. In this case, our first term is 2, so we want our first exponent to be 0. 3 to the 0 is 1. So our exponent is going to be n minus 1. This is the general form of a geometric sequence. A times r to the n minus 1. To get from one term to the next, we always multiply by r. So a is the first term, and r is the common ratio, the number that we multiplied to get to the next. Here's an example. We can just write out the first few terms. The first one is 4, and the common ratio is 1/2, so we always multiply by 1/2 to get to the next term. In this one, the first term is 3, and we're always going to multiply by -5 over 2 to get to the next term. This results in an alternating sequence. This one might look a little tricky, but it's also a geometric sequence. What we can do is use exponent rules to make this look like the form that we want. The numerator, we don't want 2n, we want n. So we can say this is the same thing as 3 squared to the n, or 9 to the n. The denominator, we don't want n plus 1. We would rather have n minus 1, but we could first start off by making it n, so it's the same as the top. So 2 to the n plus 1 is 2 to the n times 2 to the 1. Now we can bring out the 2 to the 1 in front, because it doesn't have an n on it. And at this point, if you like, you can make this into n minus 1 instead of n, but we can see the ratio is 9 over 2. If we want the first term, we could always just plug in n equals 1, and you can see that it would be 4t5 over 4. That would be the first term. Or again, we can use exponent rules. Change both the numerator and the denominator into 9 to the n minus 1 times 9 to the 1. Remember, we want n minus 1, so subtract 1 from the exponent and then multiply it by 9 to the 1. If you're not convinced, just think about what you would do to those two exponents if you were multiplying the powers together. You would add them up and you would get n again. Then you could bring the 9 over 2 to the 1 out in front to get 45 over 4, and 9 over 2 can go together. It's n minus 1. And that is definitely the form of the geometric series or sequence that we like. Now, a geometric series is what you get when you add up all the terms in a geometric sequence. Now, a geometric series is always going to converge if r is between -1 or 1. And that's a theorem you have to remember. Not equal to -1 or 1, but between them. And this is one of the few types of series that could actually give you a sum. There's a formula. If you have a geometric series and r is between -1 and 1, then you can calculate the sum. It's an infinite series, but you can calculate the sum. It's a over 1 minus r. So that's another thing that needs to go into your brain. Examples would be asking if a series is convergent or divergent, and if it converges, then find the sum. This series is a geometric series. R is E, and E is greater than 1, so the series diverges. There is no sum. Here's another example. Is this convergent or divergent? And if it converges, find the sum. So the first thing you need to do is to make this look more like the form of a geometric series that we recognize. The denominator, you need to clean up that exponent. It's the same thing as 2 to the 2n times 2 to the 1. And 2 to the 1 could come out in front. 2 to the 2n is also the same thing as 4 to the n. Just square the 2. So now we can see that r is 3 over 4. You don't have to do any more fancy tricks with exponents to make this look like n minus 1. You could just plug in n equals 1 to figure out what a is. Since r is 3/4, we know that the series converges, and we can use the formula. Just plug in a, plug in r, and you get a number. So this is the sum of the series. Telescoping series are series that, along with geometric series, you can actually get an answer for the sum. These are the only two types of series that, if they converge, you can find the sum. A telescoping series you can recognize by the fact that it's always going to be a difference of 2 fractions, sometimes a difference of 2 logarithms, but we'll see those in the examples. The first thing we do is take care of that infinity by turning this into a limit. So replace infinity in the summation with some variable and take the limit as that variable goes to infinity. We're going to deal with just the inside first. We're going to start writing out the first several terms by plugging in n equals 1, n equals 2, n equals 3 for the first several terms. You do this so that you can see a pattern. You might notice that a lot of these will cancel out. Negative 1/3 will cancel out with the positive 1/3. Negative 1/4, positive 1/4. Negative 1/5, positive 1/5. And we can conclude that the negative 1 over 6 will cancel out with a term we haven't written down yet, as well as the negative 1 over 7. What about the terms near the end of this series, when n is equal to b, or b minus 1, b minus 2? Let's write those out. We'll start with the b minus 3 term. The denominators are always differing by 2. The first denominator is always 2 less than the second denominator. So when the denominator is b minus 3, the next one is b minus 1. Or sometimes I find it's easier to start by writing out the last term, 1 over b minus 1 over b plus 2, and then go backwards. Subtract 1 from each denominator to get to the term before, until you have several terms going backwards. So here too, you can see a lot of these will cancel out. 1 over b in the last term will cancel out with negative 1 over b 2 before. 1 over b minus 1, negative 1 over b minus 1. So we're going backwards. 1 over b minus 2 would cancel out with 1 in the middle, and 1 over b minus 3 will also cancel out with 1 in the middle. So what are we left with? 1 over 1, 1 over 2. So 2 fractions near the front. That means we're going to be left with 2 fractions near the back. So this whole expression collapsed into just 4 fractions. That's why we call it a telescoping series, like those telescopes that you can pull out and then collapse when you don't need it anymore. So we can express this entire sum with just these 4 fractions. So if we want to take the limit as b goes to infinity, then the limit is simply 3 over 2. Wherever infinity is in the bottom of the denominator, we can cancel it out. And that's a telescoping series.